Okay, so the plan for today is to finish up chapter 8 and then talk about testing for the difference between two means. Uh, yes, so the question in chat, yeah, 5, 6. Yeah, so the plan for the next few days is to finish up hypothesis testing, cautions and pitfalls, the PowerPoint presentation next class, uh, possibly start correlation regression next class, or at the very latest start at the class after. So that would be a week from today, Monday the 29th. Finish correlation and regression and go through some Excel demos. We'll talk about correlation and regression is actually really a huge topic. You could spend a couple of semester long actual course going through just correlation and regression. So we're just scratching the surface. So we'll cover a little more or a little less depending on how time progresses, but we will wrap up correlation and regression at the end of class on the 1st at the latest. And then Monday the 6th will be our last class day. Note that final exam week runs Tuesday through the following Monday. So Monday the 6th is actually a last class day for like Monday, Wednesday, or Monday, Wednesday, Friday classes. So we will meet on Monday the 6th for an actual class meeting. And then Tuesday the 7th through the following Monday will be the final exam week. So we won't have a scheduled class meeting that week. But on the 8th, we'll have an optional review session from 10:30 to 12:30. So basically, I'll run this more or less like an office hours where I'll just be available at the same Zoom link as our normal class time. So the same Zoom link you just logged onto now. So that'll just be a review session, office hours kind of deal. And if more than a couple of students show up, then I'll run it a little bit more like a class session where if folks have certain topics or certain problems they want to review, we'll kind of go through it a little more like a class. Or if there's just like one person or one or two people, we'll run it more like office hours. So that's pretty flexible on the 8th there. And the reason that we have that optional review session on the 8th is just by college policy, we have to have some kind of meeting during basically our final exam time. The final exam is going to be taken on my stat lab through Examity, and you can take it anytime during the week of Friday 5/3 through Friday 5/10. So I'm giving you a little earlier than the start of final exam week to start the final exam. Just that way you have a full week, you have the weekend, if that's the time that works best for you, available. As usual, a sample exam will be posted a week or so before. I'll actually probably try to get my sample exams all up this week by maybe midweek or so. And just like on the midterm exam, you can use formula sheets and distribution tables that I posted on Blackboard in the supplemental material, exam material folder and subfolder. So that's really the plan for the last few weeks of the course. And the quote of the day today, again, has to do with margin. We had a quote dealing with margin at the beginning of the semester, but I think it's especially relevant as we move into the end of the semester when final exams and projects and presentations and so on are all kind of piling up for all of your courses. This quote by Michael Hyatt: "You must create more margin so you have room for what's important, not merely urgent." And this is definitely something that I struggle with, as I've shared before. I find myself, when I leave myself little margin, when I am right up against deadlines, on one hand, I can sometimes see that that's an impetus for me to work more efficiently and to work better. But on the other hand, it's much, much more stressful, much less of a fun person to be around. And it's much more challenging for me. So I tend to operate a lot better when I leave myself a little extra margin, whether that's, getting something prepared or getting something ready a week before it's actually due and just having it ready to go, or whether it's like leaving my house 5 minutes early to get somewhere and then I'm less annoyed at people in traffic. Lots of places that this applies, but I would strongly recommend building in a little margin as we go towards the end of the semester. And that might look like saying no to a social event or something, or maybe trying to get rid of an extra shift at work or something like that if you're able to just get ahead of things, to get your feet under you, to get a little bit in front of the work instead of behind it playing catch up. So only a couple weeks left to go. So just, finish strong, as they say, and then enjoy the summer. Okay, so finishing up chapter 8, just as kind of a reminder, we have covered 2 hypothesis tests already, the z-test from U and the t-test from U. The hypothesis testing from U when either sigma is known or when sigma is unknown. And today we're going to talk about z-test for P, the population proportion. We're going to talk a little bit about testing for difference between 2 means, and just a little bit about that. That can also be kind of a pretty big topic. We're going to just touch on one piece of that topic. And then if we have time, we're going to start into the cautions and pitfalls of hypothesis testing, the PowerPoint presentation that I popped into chat. That PowerPoint slide or the PowerPoint presentation is also on Blackboard under the supplemental material PowerPoint presentations folder. So if you need to find it later on or something, you can find it there. Okay, so with all of that said, starting into z-test for a proportion. So consider a test for a population proportion P where we have the null hypothesis P equals K, some number K, the population proportion or the probability of an event, the parameter that we're interested in equals the number K is the null, and the alternative is either P not equal to K or P less than K or P bigger than K. So we could have a 2-tail test, P not equal to K, or a 1-tail test, either left tail or right tail, similar to testing for the mean, right? Same thing applies here. We recall from the central limit theorem section that P hat is normally distributed with a mean of P and a standard deviation of root PQ over N. Note that this is a z-test for a proportion. At first glance, that might seem a little strange because if all that I have is P hat observed, you might say, well, wait, if I only have P hat observed, just the empirical number of successes for a given number of trials, I don't know the standard deviation in a sense. Shouldn't we be using a t-test instead of a z-test because I have to estimate the mean and the standard deviation in some sense? But something that we might realize is for the case of a population proportion, the standard deviation is a function of P. In other words, if I knew the mean exactly, that would mean that I knew P exactly, the population parameter P. But if I knew P exactly, I would also know the standard deviation exactly, because in this special case for proportion, the standard deviation is just a function of P. Remember, Q is just 1 minus P. So we really are only estimating one thing here. We don't, in a sense, have to pay that extra penalty for estimating a second parameter. We don't have to use a t-test with the thicker tails. We can get away with using z, our standard normal. So the test statistic is indeed z observed. And just like before, it's our empirically observed value of the estimator, if I can select it here, P hat observed, minus P naught, minus the null hypothesized value of that parameter. And in our denominator here, we have the standard error, root, in this case, P naught Q naught over N. Note that we have a little bit of a deviation from the confidence interval section here, where we would have had something like root P hat Q hat over N. Remember that in hypothesis testing, we always start our calculations by saying, assume H naught is true, and therefore our standard error is going to be root P naught Q naught or root K times 1 minus K over N, under the assumption that H naught is true. And we can, for proportion, we can take any of the 3 approaches. We could compute a p-value, we could compute a rejection region, or we could compute a critical value and use the critical value method. All right, let's look at an example. Suppose we want to test whether a certain coin is fair, that is, whether the probability of getting heads on a given flip is 50%, and we want to test the 5% level of significance. So we flip the coin 30 times and we get 21 heads. Again, at first glance, we say, well, if it was fair, kind of in a perfect world, I would have gotten exactly 15 heads. But I know that I can have a fair coin that just by sampling error, I might have happened to get a few extra heads. And that doesn't necessarily mean the coin is unfair. That was just, a bit of sampling error. But I know that sometimes, like if I got 30 heads out of 30 flips, I'd say, well, that's very unlikely to happen just by sampling error, just by chance. Therefore, I conclude that the coin is actually unfair, right? Remember, that's the basic idea of hypothesis testing. And really the question is 21 heads so far away from 15 that we say it's so unlikely to have occurred just by sampling error that we decide to move forward under the presumption that the coin is unfair? Or is 21 heads close enough to what we would expect from 15 heads that we say, yeah, I could reasonably have happened by sampling error, and I don't conclude the coin is unfair from that. So let's work through the numbers and see which one it is. Okay, so first we have p hat observed is going to be 21 out of 30. The sample probability of success or probability of heads, 21 out of 30, or 0.7. We know our hypotheses have to do with p, the population proportion, or p is the actual probability of getting heads on a given flip. We want to know if the coin is fair. So if we get, say, a lot of heads, like 30 out of 30 heads, or if we get very, very few heads, like 0 out of 30 heads, like all tails, in either one of those directions, that would be evidence that the coin is unfair, that I would want to reject the null. So my alternative is going to be that p is not equal to 0.5. P is not equal to 50%. And my null, therefore, is going to be p equals 0.5. This is a two-tail test, again, because an unfair coin can look like a coin that comes up tails way too often, or that comes up heads way too often. An unfair coin can look like one where the probability of getting a heads is very low or very high. So this is a two-tail test. And now we're going to start a calculation. So we assume H naught is true and essentially ask how unlikely is such a sample to occur if H naught was true, if the coin was fair. And let's do this two different ways. Let's use the critical value approach, just because we haven't used that one quite as much. And then we'll also compute a p-value. So we know this is a two-tail test. We can compute z observed and then find z critical and then compare. So if we look up z critical, let me switch my share here. If I look up z critical, what am I looking for? I'm looking for the 5% level of significance. So I want 5% total area in the tails. And this is a two-tail test. So I want 2.5% in each tail. I want something like the 2.5 or 97.5 percentile of z. Get my zoom right there. There we go. And again, I can kind of use this little cheat sheet down here on the z table. I could even use the t table. I could look up that number in the field or whatever, but I know that I want 5% area combined between two tails. So I'm looking for this 1.96 number here. I can also see that if I remember, I want 2.5% area in each tail, and I see again 1.96. This is a two-tail test, so this is plus or minus 1.96. And remember, my decision criterion here for a two-tail test is if Z observed is bigger than positive 1.96 or Z observed is less than negative 1.96, then we reject H naught. Or alternatively, if Z observed is between negative 1.96 and positive 1.96, we do not reject H naught. So that's really our question. So what is Z observed then? Z observed is P hat observed, 0.7, minus the null hypothesized value of P, 0.5, over, then we have a square root. Did not leave myself a whole lot of room here. So I have a square root. And here we have to be careful. Remember, it's not P hat Q hat over N, but the null hypothesized value of P, and then 1 minus the null hypothesized value of P. So it's 0.5 times 0.5 over, and the number of trials, we had 30 flips over 30. And let's plug that into the calculator. So 0.7 minus 0.5 is 0.2 divided by all of the stuff that's under the square root, which is 0.5 times 0.5 over 30. All right, so we have 0.2 over root 0.5 times 0.5 over 30. That all looks good. And this gives me 2.19. So basically, I'm saying that if I have a sample that's more than 1.96 standard errors away from the null hypothesized value for P, then I reject, and my sample is 2.19 standard errors above the null hypothesized value for P. So now I can say since Z observed is 2.19, which is bigger than my right-hand Z critical, we reject H naught in favor of H1, and we conclude the coin is unfair. Or if we wanted to say this a little in a little more verbose way, we might say something like this sample provides statistically significant evidence at the 5% level that the coin is unfair, something like that. We haven't proven beyond any doubt that the coin is unfair. We've provided statistical evidence that the coin is unfair. It is possible to get 21 heads on 30 flips of a fair coin, but it's just, as the kind of narrative said, or that we covered at the beginning of the chapter, it's just kind of so unlikely that we would need a minor miracle to explain it with sampling error, and therefore we say that it seems more reasonable to go with the alternative hypothesis that the coin is actually unfair. So at this point, we've answered the question. We would be done with the problem at this point. But again, let's just look at a different method that we could have used to answer the question. We could have used the p-value method. So we could get a p-value for this sample. Still under the assume H naught is true banner. Well, I know that p hat, the random variable, is normal by the central limit theorem. Its mean is going to be the null hypothesized value of p if H naught is true. In other words, its mean is going to be 0.5. And the standard deviation of this distribution is going to be, again, if H naught is true, the standard deviation is going to be root PQ over N, or root 0.5 times 0.5 over 30. Let's figure out what that is. I actually have that already in my calculator, more or less. We just have to delete a few characters. So root 0.5 over 30. So that's about 0.091. Now, what is our p hat observed? That was 0.7. Remember, we're doing these calculations under the assumption that H naught is true, that p is actually 0.5. If I were to reject for a sample that gave me a p hat observed of 0.7, I'd also reject for 0.71 or 0.72, anywhere further into this right tail. And any of those would be type 1 errors. I would be rejecting a true null by assumption. In this case, the null is true. If I reject it, I would be making a type 1 error. So this area in the right tail represents type 1 error. So I can say something like the p-value. Unfortunately, in stats, we name like everything p. So I'm just going to write out p-value instead of calling it p, because we've already got p for proportion and p hat and all that. So the p-value is going to look something like the probability that this random variable p hat is bigger than 0.7. But we want to make sure to take into account the fact that this is actually a two-tail test. That had we gotten a sample that was just as extreme on the other side, so instead of 21 heads, kind of 6 more heads than we'd expect, if we had gotten 6 fewer heads than we'd expect, say if we had only gotten 9 heads or 8 heads on 30 flips, that would be equally strong evidence that the coin is unfair. So I really need to double this because it's a two-tail test. In other words, I'm accounting for the fact that there is kind of an equal region on the left side, an equal sized region on the left side in the left tail that also would contribute to type 1 error here. If I reject for p hat observed of 0.7 relative to a p naught of 0.5, I'd also reject for p hat observed of, say, 0.3. I'd also reject equally far into the left tail. So that's why we're doubling this, taking into account that second tail. And we're, of course, leading on the symmetry of the normal distribution and all of this, the symmetry of the tails and everything. So we can just double this area. But I notice this is just twice the probability that z is bigger than, well, it would be 0.7 minus the mean of 0.5 over the standard error of 0.091, or that is actually just z observed. That's what we computed up here already, 2.19. And maybe here I'll use symmetry and make this twice the probability z is less than negative 2.19. I can do that, no problem. And I'm looking for an index of negative 2.1. Here it's in this row with 9/100ths is 0.0143. So 1.43% times 2 is about 2.86%. That is my p-value. That's my p-value for this sample. Remember, I'm testing against a significance level of 5% and alpha of 5%. So the p-value is my kind of actual type 1 error that I would incur if I rejected for the sample. The significance level was the maximum allowable type 1 error. So I can say since the p-value equals 2.86%, since the actual type 1 error I would get if I rejected is less than 5%, the maximum allowable type 1 error, within the constraints to be able to reject, I'm making an error less often than the maximum allowable error rate. So I reject H0 in favor of H1, and I conclude the coin is unfair. Or kind of as I said before, I could give a little more detail there. I could say something like, I conclude that, or I see that this sample gives statistically significant evidence at the 5% level that the coin is unfair. I haven't proved it beyond any doubt, but I've given statistical evidence in favor of the alternative hypothesis. Are there any questions on anything in chapter 8? Any questions on any of these tests, the z or t test for mu or the z test for p? So like I mentioned, I don't think there's really any new math or calculation or anything in here. Really the difficulty in chapter 8 is taking the kind of the math and from chapter 6 and 7, but applying it to a situation where we have to be very careful with the logic and what calculations we use where and why we do things a certain way. So I think that really is the challenge of chapter 8, hypothesis testing. Okay, I'll switch my share back to just OneNote to make it a little bigger on your screen. Sorry, I'm getting my windows back put together here. There we go. Okay, so moving forward then to chapter 9, hypothesis testing for the difference between two means. I think it's important to, discuss this at least once. But like I kind of mentioned earlier, is there are several different types of tests for this scenario where we have two different populations. And we're interested in knowing something like, are the means for the two populations the same or different? Or is one mean bigger than the other? One, kind of standard example for this is something like a drug trial where we might have a control group or a placebo group and an experimental group. And we want to know is something like, is the mean time to recovery for the experimental group, the ones getting the drug, say less than placebo? Are the people getting the drug recovering faster? Or is the mean or say the probability of recovery, the probability of reduction in symptoms higher for the folks getting the drug versus the control group, right? So we can imagine that there are a lot of scenarios like this that come up where we have an experimental group, a control group, and we want to compare some aspect of the two groups, and we want to do it statistically. We don't want to just look at the point estimate and say, oh, this number is bigger than that number, so like, yes, it's effective, or no, it's not. Again, because we need to account for sampling error. And this is one way of approaching that. We're going to look at kind of the simplest version of testing for difference between two means. There are some other tests, like I said, but we're only gonna focus on this setup here. So again, the thing that's a little different in chapter 9 is we have two populations. We have two population means that we want to know something about, and we have two samples. We have one sample from each of the populations. We're assuming we have two independent simple random samples, and that the samples both have size at least 30 or normal underlying populations. So we can use the results of the central limit theorem. Now, when I say independent samples, so we're thinking we have population 1, population 2. These are two different populations, and I sample each population individually. So I'm not thinking, for instance, maybe in another study, we might be looking at, say, a weight loss drug, or looking at the effect on an exercise program on weight loss. So I might have 30 participants, and I measure each of, say, their weights at day 1, and they go through this, maybe some of them take this drug and some of them take placebo or whatever. Or maybe they just all take the drug, and I measure their weights on day 30. And if I measure the same people's weights on day 1 as day 30, and then use those two data sets, that's not really independent data, right? That's not really two separate populations, because I have person 1 at the beginning and at the end, person 2 at the beginning and the end, and so on. So that's what we would call paired data. So we're operating under a situation where we don't have something like paired data, but where we have something more like, there are 100 people in our trial that have some condition. We split them into two groups. We give 50 people the placebo drug with no active ingredient. We give the other 50 the active drug. And then, after 30 days or something, we measure them both, and we compare the placebo group to the experimental group. So that's kind of the setup that we're looking at here. So we have two populations. They have means mu1 and mu2, which are unknown, and standard deviation sigma 1 and sigma 2. And in this case, we'll assume that we know the population standard deviations, something that we had done before just to kind of get off the ground. And then we also have two samples, one from population 1, where we have X bar 1, S1, and N1. We don't need S1 at this point, but we might need it in the future. So we have a sample mean, a sample standard deviation, and the sample size for the first group, and then the same for the second group. Something that we've talked about a little bit in the past is that since X bar 1 is normally distributed and X bar 2 is normally distributed, their difference is normally distributed. The sum or difference of normal distributions is also normal. That's that stability property that makes normal distributions special, and which is kind of the reason that the central limit theorem involves a normal distribution and not some other distribution. And in particular, this difference here, this X bar 1 minus X bar 2, is normal with a mean of mu1 minus mu2. And the standard deviation looks a little funky here. We just have to be a little bit careful with this calculation. If we thought of the variance of X bar 1, the central limit theorem would say that that's sigma 1 squared over N1. And if we thought of the variance of X bar 2, central limit theorem would say that's sigma 2 squared over N2. And it turns out that whether we add or subtract two normals, the variances always add. It is important to note that the variances add, it's not the standard deviations that add. So the variance is the sum of the two variances. And then if we want the standard deviation, we have to wrap a square root around that whole thing. So we don't want to do like sigma 1 over root N1 plus sigma 2 over root N2. That would be inaccurate. That would be trying to add the standard deviations. It's actually the variances that add. As I've kind of mentioned a couple of times before in the course, standard deviations are nice to interpret because they have units of the original data, but variances often have nicer mathematical properties. like this here, where the variances add, but the standard deviations don't add. So we often go back and forth, sometimes using variance, sometimes using standard deviation, depending on what suits us at the time. From this, we could, if we wanted to, develop a confidence interval for the difference between two means. And for the difference between the two means, we would have a point estimate for the difference between the two means, which would be x bar 1 observed minus x bar 2 observed. Here, because I've already got subscripts, I didn't write the observed, but this x bar 1 and x bar 2 are the random variables for the sample mean. This x bar 1 and x bar 2 are the point estimates, the observed values for x bar 1 and x bar 2. So these, you could give it a second subscript of observed if you wanted to. And then plus or minus some number, some z number of standard errors. So the right side looks a little messier, but we can see that it's just that same structure, right? It's just point estimate plus or minus z standard errors. What if I have a hypothesis test that I want to set up for whether or not the two means are the same? So really what I want to ask is this question here: is mu1 equal mu2, or is maybe mu1 not equal to mu2, or maybe mu1 less than mu2 or mu1 bigger than mu2? But this is really what I want to ask. I have a little bit of a problem though, because I don't know what mu1 is, and I also don't know what mu2 is. So if I think back to this P example up here, when I said assume H naught is true, because I had a null of H naught equals 0.5, I could kind of like set this anchor, this 0.5 here, and then everything kind of worked off of that center point. If I were to try to do something like that down here, I have a problem, because, okay, if I say assume like H naught is true, then like what, mu1 is what number? I don't know. Or mu1 is just mu2. Well, I have to do something that's a little bit tricky here. What I would do is I would actually just, in the null and the alternative, just subtract mu2 off of both sides. So my null then would, instead of being mu1 equals mu2, which gives me kind of like a moving target in a sense that I'm trying to look for, I can just rephrase my null in terms of the difference between the means. I'm going to call mu the difference between the means, mu1 minus mu2. And now I can see that my null hypothesis for mu, for the difference between the two means, is that that difference is 0. If the two means are the same, their difference is 0. And if the two means are different, of course, their difference is non-zero. If that was the test that I wanted to do, if I wanted to do a two-tail test. So mu1 not equal to mu2 for the alternative turns into their difference not being 0. Well, wait, this looks a heck of a lot just like what I did in chapter 8. Null hypothesis mu equals 0, alternative say mu not equal to 0, where mu, where the difference between the two means, looks like a normal with some mean and some standard deviation. And the mean and standard deviation are a little messier than they were before, but they're just some numbers. This is really just the same procedure that I did before, once I reframe it this way. Once I reframe it as the difference between the two means being 0 or non-zero, or perhaps being less than 0 or bigger than 0 for a one-tail test. And I could do the same stuff that I did before. I could look at, I could say assume H naught is true, draw the normal distribution for x bar 1 minus x bar 2, see where my point estimate is, find a p-value. I could do that. I could look at a critical region or a rejection region. I could use my test statistic for that. Again, my test statistic looks a little messier here in some sense, mainly because of this denominator with all of these kind of squares and square roots and stuff floating around. But all I would do is I would just go up here, compute my variance. I'd find a number for that. I would square root it. That would give me another number. And I just plop that number in the denominator down here. So even though it looks a little messy, we just threw that calculation off to the side. That gives me a number, 0.031 or something. And I just plug that number in the denominator, and that's that. So it looks a little scary, but it's really not that bad. We just do that little calculation off to the side. That's just some number. And actually, it's kind of nice because mu1 minus mu2 under the null is 0. Remember, we're always computing the test statistic under the assumption that the null is true. So actually, this mu1 minus mu2 bit goes away, and we're just looking at the difference between the observed sample means and our numerator. So our test statistic, the numerator, is the difference between the observed sample means, and the denominator is just that variance there, or that standard deviation that I would calculate. I calculate the variance and then just take the square root. And then just a little note down here, well, how do I adapt this to the case when sigma is unknown? Basically the same. I just use a t instead of a z, right? This would be a t interval. This would be a t statistic. I would find a t observed and a t critical. That's really the only difference. I do have to figure out how to do degrees of freedom. There is a very precise way to calculate degrees of freedom. It's kind of a big, long calculation. It's kind of annoying to do. But basically, the estimate for degrees of freedom, the kind of rule of thumb or back of the envelope estimate is, or conservative estimate, I suppose, is the degrees of freedom we just take to be the minimum of sample size 1 minus 1 and sample size 2 minus 1. We take the smaller of the sample sizes, subtract 1, use that as our degrees of freedom for the t distribution. And that's, kind of a safe conservative bet. We don't have to do a big, long calculation. This gets us what we need. Okay, so let's look at a couple examples. So here we have some heights of 9-year-old kids, and we have a sample of 60 boys and 50 girls. The boys had a sample mean height of 123.5 centimeters, the girls 126.2 centimeters. And we'll suppose their sample variances, note that we're given variance, their sample variances are known to be, their population variances are known to be 98 and 120 for boys and girls respectively. And we want to construct the 99% confidence interval for the mean difference in heights between the boys and girls at this age. And we want to answer the question at the 5% level, can we conclude that girls are taller than boys at this age? So we have to decide what mu is going to be. Do I want to do mu boys minus mu girls or the other way around? And in theory, it doesn't matter as long as we're consistent. I would rather deal with positive numbers than negatives. I don't want to risk forgetting a negative or something. So I'll do mu girls minus mu boys, because then when I do x bar, my x bar is going to be x bar girls minus x bar boys, and that's going to be a positive number. So again, my upper and lower bounds for my confidence interval, 99% confidence interval, it's going to be my point estimate plus or minus a z number times what? Times my standard error. And remember, that was this thing here. I take the variances, add them together, and then square root. So the square root of the variance for the girls, the population variance for the girls, over the number in the girls sample. plus the population variance for the boys over the number in the boys sample. Or plugging in, we get what? X bar girls is 126.2 minus X bar boys is 123.5 plus or minus. Well, we need a Z number. We need a 99% confidence interval. So let me bring up my Z table here. And again, I could use this little box down here. Looks like 2.575. Or I could say, okay, 99% in the middle means 0.5% in each tail. So I'm looking for 0.005. Or yeah, 0.5% in each tail, 0.005. And that is right here. And that gives me, again, negative 2.57 or negative 2.58. We'll go with the one right in the middle at negative 2.575. Trying to minimize this and Zoom keeps popping up. So we'll go with 2.575. And then times square root of sigma girl squared is 120. That's already the variance, so I don't square 120. 120 is already sigma squared. Over the number in the girl sample was 50. Plus for the boys, sigma boys squared was 98. Over the number in the boys sample is 60. And let's put this in the calculator. 126.2 minus 123.5. Let's do plus 2.575 times square root of 120 over 50 plus 98 over 60. And if you wanted to, you could compute the square root. You can compute the difference in the X bars and then make your what you type in a little bit simpler. You could break it up into a couple lines that way. But let me just check everything. Looks good. So this is the plus side. This is the upper bound is about 7.87. And the lower bound, I switch to a minus. I just do second enter. And then my 126.2 minus 123.5, that stays a minus. That's the difference between the two sample means, but then I need to subtract Z standard errors. So I need this plus to switch signs in front of the 2.575. And this gives me negative 2.47. So my 99% confidence interval for the difference between girl and boy heights, and this is in the direction of girls minus boys. That is important for the confidence interval. That's going to be negative 2.47 up to 7.87. And now at the 5% level, can we conclude girls are taller than boys at this age? Well, there's a couple reasons we can't just directly look at our confidence interval here. Number one, we're at the 5% level, not the 1% level, which is what the confidence interval would kind of help us out with. But also we have a different question here. Can we conclude that girls are taller than boys? This is a one-tail test. In other words, my hypotheses I'm looking to conclude that girls are taller than boys. In other words, that mu girls is bigger than mu boys. And I'm testing that against mu girls equal to mu boys, which of course encompasses all of the mu girls less than or equal to mu boys. If I can reject against this borderline null hypothesis, I can reject against any other null that's further into that tail. Or if mu equals mu girls minus mu boys, then my hypotheses look like, well, H naught becomes mu girls minus mu boys equals 0, or just mu equals 0. And H1, I have to be careful here. Mu girls minus mu boys, mu is bigger than, because I'm subtracting the mu boys over 0. I need to get that direction correct. In other words, I have a right tail test. I can come down here and say, assume H naught is true in this sense over here. Then I have a random variable X bar, which is X bar girls minus X bar boys. It's normal. If H naught is true, it has a mean of 0. And it has a standard deviation of, well, that was that complicated square root of all that stuff. We're not super worried about what it is right at the moment. But it is centered at 0. And now I want to ask, what is X bar observed? Or this is X bar girls minus X bar boys. I need to make sure, just to stay consistent. It doesn't matter which way I pick girls versus boys or boys versus girls, but I just have to make sure to stay consistent through the whole problem. And these are both observed. Just to be clear about that. And that is 126.2 minus 123.5. Or 2.7. So my best guess is that the girls are on average 2.7 centimeters taller than the boys. But again, could that just be due to sampling error? Maybe. So that's what we're looking for here. So here's 2.7. This is a right tail test, a one tail test. I would only reject the null in favor of the alternative. I would only conclude that girls are taller than boys on average if this X bar observed is far to the right. If I got a sample where the boys were taller than the girls, I certainly wouldn't conclude from that that the girls are taller than the boys. So this is a one tail test. And I guess I'll compute a p-value here. I will go back to calling it p because we don't have so many p's floating around like we had in the proportion section. This is the probability that the random variable X bar is bigger than 2.7. Or it's the probability that Z, a standard normal, is bigger than 2.7 minus the mean of 0 over, all right, let's compute the standard error now. This is going to be, I have to add the variances. So this is sigma squared girls over number of girls plus sigma squared boys over number of boys, all under a square root. So this is square root, looking just up above on the calculator, is 120 over 50 plus 98 over 60. All right, that was the right numbers, right? 128 over 50, 98 over 60, yeah, looks good. Or that's right on 2. All right, 2.008, we'll just call it 2. Or this is the probability Z is bigger than 2.7 over 2. 1.35. I should have done that in my head. I'm used to these numbers not looking nearly this nice. And of course, this is the same as probability z less than negative 1.35 by symmetry. And we can go to our normal table. Probability z less than negative 1.3 is in this row. And we're looking for the 5/100ths. We see that that's here, and this is 0.0885. My p-value is 8.85%. My significance level I'm testing against is the 5% level. In other words, if I were to reject the null in favor of the alternative and conclude that girls are taller than boys at this age, I would make a type 1 error 8.85% of the time, but my maximum allowable type 1 error is 5%. So since the p-value, since the actual type 1 error rate is not less than the maximum allowable type 1 error rate, the significance level, we do not reject H naught, and we cannot conclude girls are taller than boys. This sample fails to provide statistically significant evidence that girls are taller than boys. Or in other words, this difference in the average heights could reasonably have occurred just by sampling error. It's not big enough that we can say it's so unlikely to have occurred by sampling error that it makes more sense to move forward, presuming that girls are taller than boys at this age. This could reasonably have just happened by sampling error. This sample does not, whoops, what did I do there? This sample does not provide statistically significant evidence that girls are taller than boys. Even though our point estimate, at first glance might suggest so. Any questions on any of this? And of course, just like before, we could also do critical value method or rejection region method. Both of those would, be equally valid approaches to answer the same question. All right, so example 2, driving speed of male versus female drivers. Here we have a sample of 18 versus 27, females versus males, average speed 68 and 70 miles per hour, and standard deviation. So we have to be a little careful here. We're given standard deviation, not variance. So when we want variances, we will have to square these numbers, 2.5 and 2.2 miles per hour. At the 10% level, can we conclude there is a difference in mean driving speed of males versus females? So again, I would like to, it doesn't matter which way I set my mu up, whether it's males minus females or females minus males. I probably want to stick with the setup that gives me more positive numbers because it's just easier to deal with. I don't risk dropping a negative. So I'm going to set mu to be mu males minus mu females. That way, when I do my X bar observed, it's going to be 70 minus 68 or positive 2, and I just don't have to worry about accidentally missing a negative. My null hypothesis, or my null hypothesis, is going to be that mu males equals mu females. And my alternative, note that I ask, is there a difference in the speed? Mu males not equal to mu females. And as an aside, I think I mentioned this before, but when I'm developing my hypotheses, I don't look at my data first, right? I mean, when you're given a problem like this, you're kind of given everything all at once. But if you were actually doing this experiment, you would decide what experiment you want to do. You would pick your significance level. You would decide what question you want to ask in advance. you would set up your hypotheses, you'd know everything as far as the setup goes before you collect the data. Then you collect the data and then you finish the problem. So I don't look at this and say, oh, well, it looks like at a glance, males drove faster than females, so I'm going to make this a right tail test. Right? I wouldn't say because 70 is bigger than 68, my alternative is going to be mu males bigger than mu females. And the idea is that on a different sample, I might have gotten, males mean speed is 65 and females at 66. And that would have been the other way around. I don't want to like switch sides depending on how my data came out, because the question that I'm asking, the question I'm looking to answer, is there a difference? Not are the males drive faster than females? That would be a different question. But just, is there a difference in general? And again, under this choice for mu males minus mu females, well, I suppose it doesn't actually matter here, but I would subtract mu females off of both sides. Mu males minus mu females equals 0 for the null, or mu males minus mu females not equal to 0 for the alternative. So these are my hypotheses: mu equals 0, mu not equal to 0. And here, since I did a p-value last time, I could do a p-value here, but let's do maybe critical value approach. So here I'm going to assume H naught is true. And I'm going to use the critical value method. I know that I can use Z here because I'm given sigma. So when I have a Z observed and a Z critical, well, Z critical, I have a two-tail test with alpha of 10%. I can come over to my Z table and kind of use my cheat sheet down here. Two tails, 10% error, 1.645 for my index. I can say, well, 10% total error in two tails, that's 5% error in the left tail, 5% area in the left tail. I see that's negative 1.645. I could even, again, go to the T table. If you know how to do that trick, looking at the bottom of the T table, that can even make it a little quicker. But I see it's 1.645. This is a two-tail test, so my Z critical is plus or minus 1.645. If Z observed is less than negative 1.645 or bigger than positive 1.645, I reject. Otherwise, I don't reject. So what is Z observed? It's X bar observed minus the null hypothesized value of mu over that whole standard error thing. So what is this? This is square root of sigma squared males over number of males plus sigma squared females over number of females, all under the square root. Or it's square root of sigma squared for males is 2.2. That's the standard deviation, and we need to square it. So we need to remember to do that here. Over number of males is 27. Plus sigma squared for females, 2.5 squared for the females, over number of females is 18. Oh, and as an aside, we're assuming normality here because these are small n's. I don't think I wrote that in here, but 2.2 squared over 27 plus 2.5 squared over 18 looks good, all under the square root. So that's about 0.73 or so. So we'll just make note of that number 0.73. Z observed is going to be X bar observed, or it's going to be 70 minus 68. Remember, we're doing males minus females, so 70 minus 68 over 0.73. Or we just have 2 over that previous answer. We could do it like that. And that's about 2.76. That's my Z observed. Here's Z critical. Remember, this is a two-tail test, so if Z observed is bigger than the positive Z critical, or if it's less than the negative Z critical, in either case, I'm far out into one of the two tails, I reject the null in favor of the alternative, and that is true here. Since we are far enough into the right tail, since Z observed of 2.76 is bigger than 1.645, which is Z critical, the right-hand side Z critical, we reject the null in favor of the alternative, and we conclude that there is a difference in mean driving speed. So any questions on anything in hypothesis testing, anything we've covered in chapter 8 or chapter 9? And again, there's a lot more that is covered in the book in chapter 9, but we're just kind of scratching the surface here. We just want to look at a simple example of comparing means between two populations. All right, so that finishes up chapter 8 and what we're going to cover in chapter 9. So let's switch gears here a little bit. Give me 1 second to get my screen share kind of set up here for the PowerPoint. And just in case anybody came in late, I will pop this PowerPoint in chat once again, in case you want to follow along. And it's also up on Blackboard, as I mentioned before. Okay, so for the last half an hour or so of class, more or less, we'll start into this PowerPoint. We probably won't finish it today, or we definitely won't finish it today, not in a half an hour. But we'll finish it up next time and then start into correlation and regression next class. So I think it's quite important. We looked at how to calculate confidence intervals and hypothesis tests, and we did discuss that the interpretation of them can be somewhat difficult. So the way that we kind of naturally want to interpret hypothesis tests or confidence intervals turns out to be a very Bayesian approach. For the confidence intervals, if we say something slightly inaccurate, it's probably not going to lead somebody to make a wrong conclusion. But for hypothesis tests, it really can. It's much more dangerous in some sense of the word dangerous. As dangerous as you can get in statistics, I suppose. So that's really the purpose of this PowerPoint, is to look at what are some of the cautions and pitfalls of hypothesis testing, particularly as it pertains to the interpretation of hypothesis tests. There's not a whole lot of pitfalls in the calculation and, figuring out what the p-value is or deciding whether to reject or not. most of the challenge comes in the interpretation. You have generated a rejection. What does that actually mean? What knowledge does that actually give us about the world? So the first thing that I'll start with is something that we might call problems with alpha, with the significance level. And alpha equals 5% is kind of the gold standard. It's the status quo. Most journals are going to accept alpha 5%. And if you go in and you say, I use the 10% significance level everywhere, that's going to be quite suspicious. They probably will just kick it back to you and say, redo it with 5%. That's what everybody uses. So for most journal articles, we can say that the probability that the null was rejected, given that it's actually true, or the probability that we have kind of demonstrated something noteworthy, but it's actually false in reality, is 5% or about 1 in 20. So why did people choose 5%? Why not 2%? Why not 12%? I remember as a freshman, when I was coming across hypothesis tests, I thought, man, like 5%, like 1 in 20 chance of like potentially making a big error seemed to me to be a pretty big risk to take. So like, why wouldn't we use like 1% or something? And of course, there's the trade-off between alpha and beta to consider as well. But why 5%? I mean, why not 2% or 12%? Or, why isn't there some mathematically optimal, we always use 4.735% because that's something like pi or e or something like that in the realm of hypothesis testing. That's like the best one to use or something like that. It seems like somebody just plucked 5% out of the air because it was a nice number. And that is actually kind of what happened. So the statistician Fisher, who laid the groundwork for much of frequentist statistics in the early 1900s, he wrote some very influential books. He was a very influential person in the fields. And basically for his book, keep in mind, this is 100 years ago. Everybody doesn't have a calculator, a computer, Excel, something that can just crank out p-values with no problem. So basically he says, well, if we use a p-value of 5%, the magic number for that is 1.96. Remember, that's our standard normal number here, 1.96. Or nearly 2. In other words, like this gives us a z index of 2, and that's just an easy number to work with, right? So he just basically says 2 sigma events or 2 standard error events are regarded as significant. So he's kind of just drawing a line for the purposes of the examples in his book. So is he intending to make an argument here that this is what you should use in practice all of the time? I don't know. I mean, it seems somewhat weak to me. Even more importantly, I think, is later on in this introduction, he says, using this criterion, this alpha 5%, we should only be led to follow up a negative result 1 in 22 trials, or 1 in 20 trials, more or less, even if the statistics are the only guide available. And also in another, I think it was a different book, he says, the salutary habit of repeating important experiments, carrying out original observations, a replicate, etc., shows an appreciation of the fact that the object of the study is not the individual result, but the population of possibilities. We're trying to make our experiments representative, and so on. So I think that it's clear that Fisher basically said, okay, number one, I've got to pick a p-value to use for the examples in the book. 5% is kind of a number that we can easily understand, a 1 in 20 chance of making a type 1 error that also corresponds to a pretty nice z index of just about 2. So 2 standard errors is what we need to be considered statistically significant. I don't know why this p is not italicized and that one is, but it seems like he just said, okay, like this is a convenient number. This also seems pretty reasonable, right? It's not like p-value of 30% or something, where you're making an error like a third of the time. And I think it's also important that he clearly comes from the perspective that we should repeat important experiments. But unfortunately, there's not a lot of clout in repeating the experiment that somebody else did and getting the same result. So do we just say, oh, somebody got statistical significance in this paper and give it a thumbs up and then kind of move on to the new research topic, right? Do we really repeat important experiments all that much anymore? Another note is that there's a medical literature kind of rule of thumb that for an alpha of 5%, beta is probably going to be around 20%, or the power of the test is around 80%. So a power of 80%, power is 1 minus beta, means that 80% of the time that the null is truly false, the test will pick up on that and will correctly reject it. So if the null is false, we get a rejection 80% of the time. That seems like a pretty decent power. Now there is kind of a caveat here that there are tons of statisticians who work in the medical research field, and it's quite expensive to do medical research usually. So quite often people will come to the statistician and say, I want to set up this experiment. I don't know what sample size I need. Do I need 100 people? Do I need 200? Do I need 1,000? Every additional person costs a lot of money and a lot of time and effort and so on. And potentially each person also is put at risk by the experiment, right? If it's a clinical trial for a drug or something, there might be some risk to having more people in the trial. Do we really want to put more people at risk of possible side effects? So we want the smallest number that is likely to get us a rejection if the null is actually true. So the statistician will say, okay, well, basically, what do you think your X bar observed is likely to be versus what is your null? How big is that difference? And then they'll do what's called powering the study. They'll tell the researcher, okay, to get a power of 80%, you need a sample of size 123 or something like that to give them something to go on. So there is maybe a little bit of circular logic here in that, because folks think that 5% corresponds to 80% power, maybe that's what they shoot for when they're powering their study. So then the study sizes happen to be such that 5% significance level even better corresponds to 80% power. So there might be a little bit of circular logic there, but this is the rule of thumb. Okay, so let's look at a tangible example here. So suppose that a researcher tries 400 different drugs to see if the drug causes a patient to recover faster from a certain disease. They want to test the mean time to recovery, and their null is that the means are the same. The alternative is the mean time to recovery with the drug is less than the mean time to recovery without the drug, so that the treated patients recover faster. We'll use significance level of 5%. Let's suppose further that the null is true for all 400 drugs. In other words, I just chose, I don't know anything about the field. I just chose 400 random drugs from my local CVS to see, do they help treat this thing, and suppose that none of them do. Well, alpha of 5% means there is a 5% false rejection rate, or 1 in 20. So out of 400 trials, we'd expect 1/20th or 20 of them to be false rejections. In other words, if we just kind of use this throw it at the wall and see what sticks approach with 400 drugs, it would seem like 20 of them are effective, even though none of them actually are, just by sampling or just by the statistical effects. What's the probability that we get at least one false rejection of those assumptions? Essentially a guarantee. You can see how many 99 point a bunch of nines %. But let's look at a second example. Suppose again we try this 400 different drugs. The nulls, the means are the same. Alternative is that the treated group recovers faster. But now what if we square the significance level, 1/400 or 5% squared? What would this be? This would be I do my throw it at the wall approach and I get my 20 that at first seemed to look good. And then I pass those off to a colleague and I say, hey, these 20 seem to work. And they also don't know what they're doing, but they do the throw it at the wall approach and see what happens. But for them, only 1 in 20 of those is going to actually stick just by, again, the statistical chances. Well, now only one of them makes it through both of us, right? So if we say there are like 2 gatekeepers, and for a drug to be considered effective, at least according to the statistics, it has to make it through 2 gates instead of just one. Now we're knocking those initial 20 drugs down by, again, a factor of 20. That's what's happening here. So this is like following up in an important trial from an independent research team. So now alpha of 1 in 400 means that there's only going to be one drug that we think works, one that actually doesn't out of those 400. And of course, this is a little slightly hyperbolic. We're not going to just randomly give drugs to random people and see what happens, but it's not necessarily all that far from the truth when you're thinking of experiments that are right at the forefront of our knowledge. And, one researcher isn't going to just try 400 random drugs on some condition, but if we have 400 research papers or 400 researchers trying to tackle this condition, if they're all using an alpha of 5%, probably 20 of them are going to get positive results in the sense they think they found something that works, even if none of them actually have come up on something that actually works. So what's the probability of getting at least one false rejection, at least one seemingly effective drug when none of them are effective out of 400? If we have these 2 gates, it's about 2/3. So still pretty likely that one of them is going to get through, but it's not the almost guaranteed failure of the gates to keep out the bad drugs that we had before. So again, I would argue that an alpha of 5% makes a good screen. It says, hey, if you get a p-value less than 5%, this seems like a promising line of research. Let's follow up on it. But should we just all jump on the bandwagon if there's one paper that gets a statistically significant result? Maybe we should be a little more careful, a little more cautious. Now, to be fair, it might seem like, oh yeah, be a little more cautious. Don't jump on the bandwagon right away. Let's wait until more research comes out. But to be fair, there's also a cost to that. So, folks going untreated for serious conditions while we wait for research to come out is also a very real cost. So it's not an easy answer, right? Okay, the next topic, let's talk about significance versus relevance. This will probably wrap up our discussion for today, and we'll probably finish up the slides next time. But significance versus relevance. So we talked about statistical significance. We talked about compute the p-value, is it less than 5% kind of idea, right? We might compute a p-value and get a p-value that's way less than 5%. Maybe it's 1% or 1 in 1,000 or 1 in a million. It's a highly significant result. But how does that correspond to relevance? How does that correspond to importance? So suppose that we have a hypothesis test set up where the null is the mean is 100, the alternative is mean less than 100. This might be something like average IQ for folks with, some condition, or for some subset of folks. And we're looking at, does this condition seem to affect IQ? Let's suppose the true mean is actually 99.9. That's actually mu for this population. But we take a big sample of size 100,000. As we would expect, X bar is right on 99.9. Sample standard deviation is 15. If we compute the p-value, well, it's 1.75%. It's way less than 5%. It's a highly significant result. So we get statistically significant evidence the true mean is less than 100, but the true mean is actually, in reality, only 0.1% less than a hypothesized mean. The difference is significant, but is it relevant? Is it going to change anything about the interventions we give to these people or anything like that? Well, probably not. So importantly, hypothesis testing only gives a binary answer, reject or don't reject. The hypothesis test itself transmits no information about the size of the true mean. Now, of course, a confidence interval does transmit such information. So a lot of times you'll see hypothesis tests alongside confidence intervals or point estimates. They kind of go hand in hand. So we can separately transmit information about the size of the mean, but the hypothesis test doesn't really give us much in that realm. Also, beware of big data. The larger the sample size, particularly when we get into tens or hundreds of thousands of data points, which with electronic medical records these days, people can just write a program that combs through the EMR and pulls out tons and tons of data. And you can get sample sizes of tens or hundreds of thousands. So the larger the sample size, the smaller the effect, it can still be regarded significant. If n were a million instead, the p-value, instead of being 1.75 or something percent, it would be 10 to the minus 11, an incredibly small number. So p-values can be very tricky to interpret. We'll talk about that later on. There's a kind of an interesting idea with this significance versus relevance. I was listening to a podcast. I might have told you this before at the beginning of the semester. I don't remember. But I was listening to a podcast for JAMA, the Journal of the American Medical Association. They have a kind of a stats podcast. And I was driving somewhere. I just popped it on. And this guy who's an oncologist, he's a cancer doc who, most of his job is treating patients, actually deciding, what disease do you have, what stage, what are the treatment options, those kind of things. But he obviously needs to keep up with the research. So his main job is not being a researcher, but treating patients, but he wants to keep up with the research. So the interviewer asked him, like, basically, there's so much information that comes out these days. How do you decide, I'm going to read that paper, I'm not going to read that paper, right? You don't have time to read them all. How do you decide? And he actually said, one of the ways that I decide is I look at the sample size. And if the sample size is very large, I don't read that paper. And it seems shocking. You're like, wait, aren't large samples good? And he's talking about, not just sample sizes where they comb through the EMR, but where they have actually treated patients or something like that. And his argument is, well, as a clinician, the most important papers to me are the ones that will change my clinical practice, that will change the treatments that I offer to my patients or the suggestions or advice I offer to my patients. So I'm looking for clinically relevant information. So there's this concept of a minimally clinically important difference. Is an oncologist going to change their recommendation to their patients or their practice if something is, 0.1% more effective? Probably not. And his argument is related to the significance versus relevance and to the power idea, that if to power your study, you need like hundreds or thousands of people, of participants, that probably means that you expect that your actual difference is very, very small. So you need a huge sample to detect that difference. And huge samples are very costly. You wouldn't just use a huge sample for no reason. So his point is, when he sees a large sample, he thinks, okay, this researcher went to their statistician, said, I want to power this study. And the statistician said, what effect size do you want? And they said, it's very, very small. So the statistician said, okay, you need a very, very large sample size to detect something that small. And that means that difference probably falls below the minimally clinically important difference for that physician. So that's not really a worthwhile paper for him to read. He moves on. So it seems very counterintuitive at first that he ignores large sample size papers. But that's his argument. And I think it's a very interesting argument, particularly as we get to significance versus relevance, that he's arguing, okay, in order for you to get statistical significance, you need such a large sample size that the actual difference in the means between the hypothesized mean and the observed mean is probably very, very small. And it's not going to change my practice. My time is better spent elsewhere. Now, for somebody whose primary job is researching in that field, maybe they ought to read that paper. But for a clinician whose main job is giving the best advice to his patients, that one is not super important to him. Okay, so I think we will stop there.